In the last video, um, we saw that how the reaction rate decreases over time as the concentration of the reactants decreases. And this decrease in concentration depends on the order of the reaction. Now, in this video, you will see or you will learn how to use the integrated version of the first and second order rate laws to predict the concentration of a reactant at any time, and how to use the concentration of a reactant to determine how much time has passed since the rate of the reaction. So let's start with the first order reaction. And again, I'm taking a general reaction. A is a reactant producing product. So, and remember what the first order reaction was, that as the rate doubles, the concentration of the reactant doubles too. So the same thing, if the concentration of the reactant gets halved, then the rate gets halved too. Um, so first order reaction, A gives product. So what will be, how will I be writing rate is equal to, one way is to write down like that, change in concentration with time, and with the rate law we saw, we can write down K times A raised to the power 1 because it's a first order reaction. So let's rearrange. So we're gonna just use these two. That means my Ka, or let's say write down back to delta A over delta T, and I'm moving the negative sign on the other side. And then I will bring this here and this on that side, which is change in concentration over the concentration of A equals negative K delta T. And so if I integrate it, it will be ln A over A naught equals negative KT. Now from here to here I went by integration, so you do not need to know the whole integration part, but this is what you need to know, that if I rearrange this equation, it will be ln A minus ln A naught equals negative KT, and if I bring it on this side, it will be ln A equals negative KT plus ln A naught. So this is your first order reaction equation. What does this tell you? If you compare it with your linear equation, what does that tell? That if you draw the graph, that means ln A naught represents the y-intercept and negative k will be the slope. So that means if you will draw the graph between time, because t is on my x-axis, versus ln A, concentration of A, ln A at a particular time, then it should come out a straight line with the negative slope because it is negative here, and then the slope of this line will be K. So this is another way to find out whether your reaction is first order or not. You can use concentrations at different times, draw the graph between ln A and time, and if your slope comes out a straight line with a negative slope, that means it's a first order reaction. Now half-life is the amount of time it takes for 1/2 of a reactant to be used up. So let's say if you started with 4 molar of your reactant, and then when 2 molar is left, how much time it takes for it to be half. So again, we are still discussing the um, first order reaction. So ln A equals negative kT plus ln A naught. And what are we saying now? That see, this A naught means initial. Initially what you started with, concentration of A, and this is after time t. So now we are saying that half of the reactant is left after how much time. So that means I should say half of this is left, half of initial, and that time we're going to call it as T half plus ln A naught. And again, with all the rearrangements and everything, you will see that your answer will come out T half equals 0.693 over K. That is your half-life. What does that mean? That means to find the half-life in the first order reaction, you just need the value of K. It is independent of the concentration, the half-life. So this graph here, if you have a graph like this with the concentration and time, and these are the different points, I have to 0, 100, 200, 300. So in this case, if the total reaction is taking 300 seconds, half of 300, or let's say I have to put, let me make some values here, 50, 100, this is molarity, 150 and 200. Let's say we started with 200 at time 0, and half of 200 is 100, which is here. So the time it takes from concentration to change from 200 to 100, that is my T half. So this is my 100. So how much? 150 seconds. You can also find it graphically. This problem number 8, the formation of nitrogen dioxide and oxygen is given. It is first order in NO and first order in O3. That means if I have to write down the rate, it will be K times concentration of NO raised to the power 1 times so they are first order in NO as well as in O3. Now if the concentration of NO was increased by half, so here is the concentration of NO, now it is increased by half, that means the new concentration will be 1.5 times NO. We're talking about concentration. Similarly, they said if the concentration of ozone was quadrupled, that means if the concentration of ozone is O3, then quadrupled means 4 times O3. So that means my new rate will become K equals concentration of NO, which is now 1.5 NO times concentration of ozone, which is 4 times ozone. That's my new rate. And if I multiply 1.5 with 4, it is 6. That's the new rate after the concentrations were changed. The question is by what factor? So to find the factor, it is 6 times. You can just look it like that to find the factor, new rate over old rate. 6 NO3 time divided by old rate, which was NO over O3, or you can simply say 6 times. So this is cancelled out, equals to 6. Next problem. In this one, the reaction is given A plus 2B gives C. Now class, these two here or one here has nothing to do with the order of a reaction. Order of a reaction you always find out with the rate. So the very first thing you have to do is to find the rate law, and remember the rate law for the rate. In this case it is K times A raised to the power M times B raised to the power N, and I have to find the values of K, M and N. So we always start with M and N. To find the value of M, the order of a reaction with respect to A, I will pick the two experiments where the concentration of B is not changing and where I can see it's here. Experiment number 1 and 3, B is same but the A is getting doubled. And if A is getting doubled, look at the rate. What is happening to the rate? It is getting 4 times. What does that mean? That means the rate of a reaction with respect to A is second order. That means M is 2. Because if I double the concentration of A, the rate becomes 4 times. That happens in the second order reaction. Let's find the value of N, the order of reaction with respect to B. In that case, we're going to pick two experiments where A is constant. Here, the concentration of A is constant here. And if you look here, if the concentration of B is doubled, the rate is doubled. What does that tell me about N? It means it is 1. So now we got the rate values. My rate law is K times A second and B to the power 1. Now I can pick any one experiment. Let's say if I pick the first experiment, I can plug the rate value, which is 1.2 times 10 to the negative 4th equals K, times concentration of A is 0.12 raised to the power 2, times concentration of B is 0.010 raised to the power 1. So by dividing both sides with this value, I can find the value of K, and that value of K for this reaction should come out 1.2, and this will be the unit. So then in my rate law, my final answer will be rate equals 1.2 times A to the second B. That will be my final answer, 9A. Let me write down here final answer the way you will see in the multiple choices. That will be the final answer for 9A. Now 9B, calculate the initial rate for the formation of C at 25 degrees Celsius if concentration of A is 0.50 and concentration of B is 0.075. So this is, for the question like that, all you have to do is, you know the rate law, you just have to plug these two values. A is 0.50 raised to the power 2 times 0.075 raised to the power 1, and if you will solve it, it should be this. Let's discuss the second order reaction equation. In the second order reaction, remember, if the rate is doubled, the concentration is quadrupled, means 4 times. So rate equals to Ka to the second. Rate is also equal to negative delta A over delta T. So again, I'm going to make this equal to here, and after rearranging it using the calculus, you will see your final equation will come out this. Where A is the concentration at any time t, A naught means the initial concentration, K is the rate constant, and T is the time taken. If you, in this case, compare it again with the linear equation, that means I should write down like this: 1 over A equals KT plus 1 over A naught, which means if you're drawing a graph between time and 1 over A, it is not A, 1 over A, here, you're going to have a straight line. You can find out the slope of this line, and the slope of the line will be K. So again, if you are given the concentration of A at different time periods, you can draw the graph between 1 over A and time, and if it comes out a straight line, that means it's a second order reaction. Now, half-life and second order reaction, this is the 1 over A equals to 1 over A naught plus KT, that is the second order reaction. And again, what is half-life means that when this A changes to A naught over 2, A naught is the initial, then we use T half. So if you're going to rearrange equation and replace A with A naught, finally you will get T half equals to 1 over K A naught. And I think on the last slide I have all the formulas written on one slide, so that you don't have to go back and forth to look for the formulas. So that means if you look in this second order reaction, the half-life depends on the concentration, while in the first case, in first order reaction, it was independent. So this is the way you calculate the half-life for the second order reaction. Now look at this problem. A certain second order reaction has a rate constant of 1.90 times 10 to the negative third and initial half-life of 256 seconds. So the question is, what is the concentration about one half-life? Means about one half-life means when the concentration is half of what we started with. So how do you do this question? All you have to do is to use the formula for second order reaction, because this is second order. So you have T half equals 1 over K A naught, rate constant, this is the value of K. Initial half-life means they gave you T half, 256 seconds, and now you have to find A naught. So solve this question, and then we can discuss the answer for this in the class. Zero order reaction, your rate is independent of the concentration of the reactant. Whether you increase or decrease, it will not make any difference. So if you have, so rate is basically equal to K. So which means, what is rate? Negative delta A over delta T equals K. And so your equation becomes concentration of A at time t equals negative Kt plus A naught. Compare it with y equals mx plus b. So if you draw the graph between time and concentration, you get a straight line here with the slope of negative k. So this is the summary. First order reaction equation written in terms of natural log. You can get rid of natural log and to get the equation in the exponential form. Remember, ln is opposite of exponential, and if it's a first order reaction, the unit of k, rate constant, always comes out per second. Second order reaction equation and unit of rate constant always comes out this for the second order reaction. Zero order reaction, this is the unit and this is the equation. Problem number 10. The rate constant for a certain reaction is given. K equals to 8.00 times 10 to the negative third. And if the initial concentration was 0.500 molar, what will be the concentration after 19 minutes? Now, how will you know what kind of reaction is this? First, second, 0 by the unit of K. This shows that the reaction is first order with respect to the reactant. So you can use ln equation or A equation. So if you use this one, A equals A naught e to the power negative K naught. Your A naught initial concentration that we started with is this, e raised to the power negative K value is given 8.00 times 10 to the negative third times time. Now unit has per second, so you have to change 19 minutes to seconds by multiplying it with 60. So equals to 5.47 times 10 to the negative fifth. That will be the answer. I can go back to the last slide where it was, I think, this question, problem 9C. I can give you the answer for this one. The answer, once you're going to solve it, should come out 1.03 m. The last question for this video. A zero order reaction has a rate constant of 1.80 times 10 to the negative fourth. If after 60 seconds the concentration has dropped to 9.00 times 10 to the negative second, what was the initial concentration? Now again, for this one, the first thing is you need the formula, and for zero order reaction, this is my equation. Concentration of A at any time t equals to negative Kt plus A naught. So I'm going to write down this equation here. Concentration of A, which is my reactant, at any time t equals negative Kt plus initial concentration. So now constant rate. So this is K value 1.80 times 10 to the negative fourth, and then it says after 60 seconds, means it is 60, and after 60 seconds the concentration has dropped to this. That means this is the concentration after 60 seconds, which is 9.00 times 10 to the negative second, and the question is what is the initial concentration. So multiply these two, take it to the other side. Your A naught should come out 0.101 molar.